So welcome. So this next section we're going to use what we learned about energy. And there's really three things we're going to do in this section. So we're going to do conservation of energy when there's no friction. Then we're going to do energy when there is friction. And we're going to compare and contrast those two. And then we're going to look at power, which is a bit of an aside. It's kind of the next thing. They just put it into this chapter. Think of friction as being, so we have mechanical energy. We have mechanical energy, and we have, if you like, we have kinetic energy, we have gravitational potential energy, and we have gravitational spring. We have a spring potential energy, and those are mechanical energy. And if there's no friction, they're trapped. It's like having money in your bank account. You know, you have a savings, a checking, and a retirement, whatever you want. And sometimes you move money around, but unless you're taking money out or you've been charged fees, you get the same amount of money. It might be in different places, so you can just swap it around. That's the world without friction. If you have friction converts some of this energy into thermal energy. And that radiates away. And it's hard to get back. So it's a bit like bank fees. You know, you got the money in the bank. When I moved to the States, I had this very small amount of money in a British bank account. And I kept meaning to send them a letter to close the bank account down. And it was just one thing. It was always like there was other more important stuff to do. And basically over a period of probably, I forgot about it for a while. So over a period of about, I don't know, maybe 3-4 years, they took my $20 away, you know. But in the end, I ended up with no money in my bank account, you know, because of friction, bank fees, you know. So it's like that. So that's where we're going. So we talk about isolated systems. That's one with no friction. We talk about non-isolated systems. So this is no friction. Where does that term come from? Well, remember what we had. We had a mechanical system, and when you have friction, then the energy kind of goes to thermal. If this is isolated, that doesn't exist. So that's where that terminology comes from. When you're isolated, there's no escape to thermal energy. So no friction. Non-isolated systems means there is a path to thermal energy. So you're going to lose stuff. And then we talk about average power, instantaneous power, and power conversion. So we'll talk about that. So kind of 3 bits on this. Conservative forces versus non-conservative forces. For conservative forces, the work done depends upon the initial and final coordinates. Work done does not depend upon the path taken. Okay. So if here's the bottom of the mountain, there's the top of the mountain, and I go like that, there's a certain amount of work done. If I go like that, there's the same amount of work done unless there's friction. If there's friction, this short path has less friction than this long path. So it's important to realize, is there friction or not? If there is not friction, what you put into the system on the way up, you get back on the way down. If there is friction, what you put into the system on the way up is more than you store because you're paying to overcome friction. And when you get back is even less. So conservative systems, and good examples are gravity and springs, electrostatics. Conservative systems, no friction, happiness. If an object moves through a closed path, the work done by the conservative force is 0. What you put in on the way one way, you get back on the other way. we tend to live in a friction-filled world, and so it seems like we're getting something for nothing, when in reality we're just not having stuff taken away from us. We get so used to having stuff taken away from us that when the stuff is not taken away from us, we feel like we're ahead. We're like, I don't know if you remember Al Bundy from Family Matters, but that was a guy who basically was so ground down by life. When nothing bad happened, he felt like he was ahead, and always bad things happened to him. It's like, it's like very dark humor, really. Non-conservative forces work done depends upon the path taken because there's friction, and you pay for any kind of change. Going up, going down, you're going to pay. Okay, so conservative forces give you an isolated system. So conservative forces give you an isolated system. Non-conservative forces give you a non-isolated system. Object does not interact with its environment. There's no progress to heat. In an isolated system, energy does not cross the boundary of the system, does not go to heat. Mechanical energy is conservative. This occurs where there is no friction. There's the takeaway. And non-conservative system, the object interacts with its environment. In non-isolated systems, the energy can cross a boundary. Work kinetic energy theorem applies. This occurs when there is friction. My change in my mechanical energy is equal to my change in kinetic plus my change in my gravitational potential plus my change in my spring potential equals 0. In an isolated system, in a system of conservative forces, there's no change in the mechanical energy because there's no friction. You might change where it's put. Maybe all the kinetic goes to spring potential because you're squishing a spring in. Maybe all goes to climbing a mountain. But the fact of the matter is what's given up by one thing is taken by another thing. In a non-isolated system, in a system where there is non-conservative forces, then we have my change in my mechanical energy and the work done by frictional force equals 0. So we have to include this frictional bit. Because, energy is neither created nor destroyed, but if it goes to thermal energy, you don't get it back. So, your $100, my $20 is still out there somewhere. Just the bank has it, whereas I had it. It was like they took it from me through fees. They took it from me through friction, if you like. Still there, still exists. Got to account for it. If I account for it, the change is 0. $20 is still there. But it's just somebody else has it now. So mechanical energy is the sum of kinetic energy, gravitational potential energy, and spring potential energy. And just remind ourselves that this is half mv squared, mgh, and a half kx squared. So a little bit of playing first of all. A student plots a graph of kinetic energy versus speed. Which trace should she see? Will you answer that one for me, please? Because I noticed when he practiced at this through these graph things. So write down the equation. Write down the equation. Linking kinetic energy. So here I'm calling it UK. So K equals UK, whatever you want to call it. Write down the equation linking kinetic energy and speed. Speed is V, So what's the equation? And then look at your graph. And on your equation, carefully circle only the symbols that are on the axes. And then ask yourself, what's that relationship mathematically? If that doesn't work, put numbers in to get it to work. And then vote. So we've got about 28 people here today. Let's try and get into it. A couple more people. If you're not going to do it, just put down a number of a guess. I'll give it until 45. So let's have a look. Let's stop it in a second. Stopping it now. Okay. So what did people say? People said, oh, mainly E, but there's some D there. So let's be careful with this. So let's have a look. So the equation, of course, is that KE equals 1/2 mv squared. We got that bit. And then this is where people tend to mess up a little bit. Well, K, there's one axis. That's my y-axis. But my x-axis is not v squared, of course. It's v. Okay? It's not v squared. It's v. So this is not a linear relationship. If it was k versus v squared, that would be linear. But you're not plotting v squared. You're plotting v. So this is going to be E. So if you can't see that, then what I suggest you do is you go K and V. Actually, I'm going to do three columns for this. V. And you are plotting V and K. So you say, well, let V equal 0. Forget what M is. Call M 1. I don't care. Call M 2 and 1/2 times 2 is 1. It doesn't matter. It's not changing. So V squared is 0, so K is 0. If you call V 1, 1 squared is 1, so K is 1. 2. 2 squared is 4, so that's 4. 3. 3 squared is 9, so that's 9. So when you plot this, K versus V, 0 was 0, 1 was 1, 2 was 4, oh, not there, but there. 3 was 9, oh, not there, but there. And you can see that that's that relationship, yeah? So it's going to be E. So some people can just see it from the equation. Some people need to do this graph. Later on, Physics 2, I like to give you the challenge of plotting the graph. And people say, what numbers do I put down? And I turn around and say, I don't care. You just got to put numbers down. And I can figure out the ratio. I can tell you if it's right or not. But you got to, and people are very uncomfortable picking their own numbers. You've been trained for years to put the numbers from the question into the formula. And when you're allowed not to have numbers, people kind of like don't know what to do. It's like, you know, you've been locked in a room for 20 years and the door's open and you can go where you like, and people stand there for a long time going, I don't want to go out there. You know, it's kind of like, yeah, it's like, but that's engineers. You're not going to have your job, unless you become a teacher, is not going to be solving problems from the back of the book. Your job will be turning around saying, what matters? Not what's in the question, what matters? What numbers are there? What's the relationship? So kind of, let's try and get a little more used to just, you know, kind of like developing. Can you ever go at number 2, please? The middle one. Oh, yes, can you ever go at the middle one, please? Remember, write down the equation, circle the two axes. That's what people miss out, is they don't circle the two axes. And so they tend to, it's all in their head, and they make a mistake from it. So circle the axes. I'll give you until a minute on this one. Let's go. And then let's see what people decided. People decided mainly D. So let's have a look and see how that comes from. So, boom, boom, boom. So let me go back to my red pen color. So for this one, student plots a graph of potential energy. So UG is equal to MGH. And we're plotting. So let's figure out what we're plotting. We're plotting UG, that's on that side. And we're plotting H on that side. That's linear, isn't it? You can see that. The M and the G are constant, so that's going to be linear. And again, if you weren't comfortable with that, you'd go, well, there's UG, and then you'd go, there's H. Let everything, if it's not changing, call it 1. MG, call it 1. So if that was 0, that would be 0. If that was 1, that was 1. If that was 2, that was 2. UG versus H. What I say in physics 2 is draw me a graph plotting at least 3 points. Boom, boom, boom. You've got to put the numbers down for the 3 points. I'll do the next one. So for the next one, we're going to have, let's have a look. We're going to say US equals 1/2 kx squared. Let's have a look. What am I plotting? I'm plotting US versus x. Not x squared, but US versus x. So US, and let's have x squared, and that's x. So I start off and I say, well, let x equal 0. 1/2 k, let that equal 1. So 0 times 1 is 0. That's 0 squared, which is 0. And then that's going to be 1. 1 squared is 1, which equals 1. 2. 2 squared is 4, so it equals 4. And so on. So there's one axis, and there's my other axis. And I get E. Agreed? A nice skill. Block moves because it has kinetic energy of 14 joules. How much kinetic energy would another block have if it had 3 times the mass and move with twice as fast? So this is a ratio problem. So we visualize, here's a mass, here's a velocity, and it's got a certain amount of kinetic energy. K equals 14 joules. And then we have another one. Doesn't matter how you draw it. I'm going to draw it bigger, and M. Let's call this M old and M new. And then let's call this V old and V new. And then we have K old and K new equals. So I'm doing the ratio of the new to the old. I've learned the hard way that you always put down. So what's the equation? KE is equal to 1/2 mv squared. So KE new over KE old is equal to my KE new over, I know the old is 14. And that equals 1/2 times M new V new squared over 1/2 M old V old squared, which equals, well, 1/2 and 1/2. They're going to go away. Then the M new, it says another block which had 3 times the mass. So M new is 3 times bigger than M old. The easiest way to do that is to call it 3 and 1, isn't it? You could have used 9 and 3 or 27 and 9 or whatever you want. 3M and 1M, as long as you put M's on top and bottom so they cancel. What people will do is they'll put down 3M and 1, and then they have an M in there and they don't know what to do with it because they've made a slip. So keep it simple. It's 3 to 1. 3 and 1 is the easiest way. And then twice as fast. So that's going to be 2 and 1. But remember, you've got to square those. So that's going to be, the halves go away. Everything on the bottom comes to 1. So 2 2s are 4, 3 4s are 12. Amazing number of people will tell me that the answer is 12 joules. And it's because they're not thinking in equations, they're just doing things in the head, and they didn't bother writing down k nu over 14 equals this. They just worked out the arithmetic. Well, yeah, k nu over 14 equals 12, so k nu is equal to 12 times 14, which equals 140 plus 28 is 168. You know, if you come to my house, you will see that my bits of the house, the bits that I'm in charge of, like my desk, is a disaster. If you come to my office, which I recommend you do, especially if you're not getting the results that you want, if you come to my office, you'll see that my desk is a total, I mean, it's kind of like, it's like an archaeological dig. Okay, I am not by nature a neat person. I am not by nature somebody who dots the I's and crosses the T's. I don't have to straighten things on my desk. I just don't notice it. I remember giving somebody a ride to the airport, and they dressed up to fly. They were in this immaculate clothes. And remember, as they sat down in my passenger seat, I suddenly saw all the dirt that was on that passenger seat. Bits of food. I'd never noticed it. And then when they're sitting there, I'm thinking, oh man, they must be like, want to get fumigated when they get out of the car. I don't notice stuff like this, and yet I do this. I am careful about this because it irks me to put that down as the answer and lose points because it's wrong. It's not a near miss. It's wrong. The bridge fell down, the car crashed, the airplane burned. It's wrong. And if that happens, you can't just show your notes and say, oh, look, I just made a slip. You know, I'm sorry the bridge fell down. It was just a slip. What was I thinking of? So there's an onus on us, just like doctors are allowed to kind of vaguely know the pills and then, wipe out a population. We're not allowed to vaguely be able to do the math and, have people just plummeting off the edge of a cliff. So we got to develop ways of prospering in this. And if you're getting the right answer, doing it in your head, great. But I'll tell you, by the time you get to 40, that's not going to work anymore. If you're not getting the right answer doing things in your head, stop. This is not hard stuff. You do harder stuff than this every day of your life. It's just that it's new. And when you're driving, you learn to stick in a lane, not vaguely go around the lane. You learn to look at all the axes. You didn't only look one way because, hey, who cares about something the other way? You know the methodologies to survive. Yeah, didn't when you first started, but you learned. You need to, if you're not getting what you want, you need to copy from somebody. And modestly, I'd say, why not copy from me? Because I was not a natural student of this. It's not that I could always do this. I learned to get better. And you can learn to get better. You just got to recognize you need to. I've been doing it for 20 years, so by now it's kind of like, it's a bit unfair because it's like, you're not seeing me as I was. But, I was not somebody who found all this stuff easy. Let's do some bit more interesting examples, and I'm going to do a couple here. So they tend to ask about pendulums, because there's not much air resistance, and they tend to ask about roller coaster rides. And then the other thing they'll talk about for the non-isolated systems, for the frictional systems, the classic is you're going along ice and then you go along rough snow. And if you've ever been skiing in the northeast, there's a lot of ice and then there's rough snow. If you go skiing in the west, they have a lot more powdered snow apparently. I've never been skiing in the west. I didn't go. I was there and I didn't go. And it was a real shame because from what I gather, it's a completely different, it's very nice. It's like it's different. Okay, so let's just play with some of these. So we have a pendulum. I'm showing you 3 points of the pendulum. Pendulums, of course, go equal one way and the other. So I'm not showing you all the journey. I'm just showing you 3 points. Pendulum swings from A to B to C, and then goes on. But I'm just showing you A, B, C. A, it has a UG of 7 and a kinetic energy of 0 because it's the extreme. So I know that's the extreme. So I'd go UG equals 7 joules, K is equal to 0 joules. And I ask you some questions. What is its EM? It's mechanical energy. So it's EM. Well, EM is equal to K plus UG, I suppose plus US, but there's none of that around. So that equals 0 plus 7. Oh. EM, mechanical energy, is equal to 7 joules. It's just adding them up. Just adding them up. Now, if I know the mechanical energy at point A is 7 joules, I tend to call it ME, but I'll call it EM, is equal to 7 joules. Then I know it's 7 joules everywhere because there's no friction in this. What is the kinetic energy at B? Well, B is at the bottom of the swing. I can tell that by the symmetry. It's the vertical bit. So I say that, well, EM is equal to K plus UG plus US. Forget about that US. So we say 7 is equal to K plus my US, my UG, my gravitational potential energy there is 0. It's the bottom of the swing. So K is equal to 7 joules. And then what is the UG at point C? Point C is neither the extreme nor the middle of the swing. So I say, well, my mechanical energy equals K plus UG plus US, but there's no spring around. So my 7 is equal to, at this point here it says that my K is 2. 2 plus UG. So my UG is equal to 7 minus 2, which is 5 joules. Simple as that. Boom, boom, boom. So what am I using? Mechanical energy is equal to the sum of kinetic, gravitational potential, spring potential. That's what I'm using here. Can you have a go at that the first part for me, please? And we're back. Let's stop this. Let's see what most people are saying. Most people are saying B. Let's have a look. What I say, of course, is that my mechanical energy is equal to K plus UG plus US, but there's no spring in my question today. So my mechanical energy, and that's what it's asking for, EM is equal to my kinetic energy, and my kinetic energy is 4 joules, plus my UG is 8 joules, which equals 12 joules. So the answer should be beyond that one. Agreed? I'll do the next one. So what is the K at point B? So here I'm at point B, where its UG is 3, because it's lower down. Its UG, its gravitational potential energy, will be less. So EM is equal to K plus UG plus US. No springs around. So mechanical energy is still the same. It's 12, and we want to know what the K is, but we're told that that's 3. So that means that the K is equal to 12 minus the 3, which is 9 joules, which is that guy. And I'll do the next one as well. So what is its UG at C, where the K is 5? So there's C. So I say EM is equal to K plus UG plus US, but there's no spring around. So again, 12 hasn't changed. In this case, I'm told that the K is 5, so K is 5 at that point, plus my UG. So UG is equal to 12 minus 5, which equals 7 joules. Cool. In principle, that's all it is. How can I make it a bit more interesting? Okay. I could tell you the mass, and I could ask you how high this is. And you'd go, UG is equal to mgh. Give you the mass, you know G, you can find the height. I could give you this information by not telling you that the K was 5, but giving you the velocity. So you'd say, oh, K is equal to 1/2 mv squared. So it's the same problem, but I say, oh, at point C you have a certain velocity. How high are you? And the linking principle is mechanical energy equals combination of kinetic, spring potential, gravitational potential. But I'm not telling you those values directly. I'm telling you how to calculate those values. So I can dress it up a bit. But the principle is this. So you know how to go from the velocity and the mass to the kinetic energy. You know how to go from the mass and the height and G to the potential energy. What we're adding now is just this conservation of energy. So that works out nicely. This is one thing I want to show you, and it's because it comes up in the books quite often, and it's a little bit of geometrical. It's like a joke. It's like a joke you don't get until you see it, and then you get it, kind of thing. So there's a little mathematical thing here that if you'd never seen, you'd be scratching your head. I was anyway, kind of going, man, where does this come from? And then once you see it, you never forget it, because it's just a little trick. So this says a pendulum swings out 30 degrees, so that's 30 degrees. From the vertical axis, the pendulum is 2 meters long, so this is 2 meters long. And what is, it has a bob of 4 kilograms, so that's 4 kilograms. And what is its speed at point B? Speed at the lowest point, so I'm going to show the speed, like, it doesn't matter about the direction. Speed at the lowest point. Is it a conservative system or a non-conservative system? There's no mention of friction, so it's a conservative system. So my mechanical energy is equal to my kinetic energy plus my potential UG plus my US. There's no springs around here. Okay, so what I can say is that my EM at C is going to be equal to my EM at B. Is that correct? There's no friction, so the mechanical energy stays the same. Agreed? So let's look at C. So at C, my mechanical energy, there's no kinetic because it's at the end of the swing. There's no spring. So this is going to be my UG at C. The kinetic is non-existent and my US is non-existent. So that's all I'm left with. And at B, we're not higher. We're at the lowest point in the swing. We got K, but UG at B, non-existent because we're not any higher than the lowest point, and there's no spring around. Oh, so this tells me that UG at C equals K at B. Okay. What is the speed at point B? So this is going to be 1/2 mv squared, and on this side it's going to be m times g times h. Well, I know my m. My m is going to be 2. I know my G is going to be 10. There's my H, but I don't know it. Let's leave it alone for a minute. I know my half, I know my 2, and I want my V squared. I got to somehow find my H. And this is the little mathematical trick that people, they don't see it until they're shown it most of the time. So there's H. And this is 2 meters, and that's 30 degrees. And the trick is that that's 2 meters. And this here would be 2 cosine 30. It's taking that 2, it's taking that 30, and it's learning the cosine of it, doing the cosine of it. And what is 2 cosine 30? Oops, let's take 2 cosine 30 is going to be, sorry, 2 cosine 30 is going to be 1.732. 1.732. So H is equal to 2 minus 2 cosine 30, which equals 2 minus 1.732, which equals 862, 0.268. So that'd be 2.68 times 2. 2.68 times 2 is going to equal 5.36. Is equal to the 2's cancel, V squared. So V is equal to the square root of 5.36. V is equal to second square root, second answer, second answer. I'm getting 2.31, I think it is, 2.31, yeah. 2.31, 2.32 meters per second. It's the same we just did in the last one, it's just that we've got to work a bit harder for it. And there's this little geometrical catch where, I don't know, maybe I know for me, the first time I saw this, I scratched my head for a fair while before I realized, oh yeah, the height I want is the 2 meters minus this, and that height is the cosine of that angle times the hypotenuse. Good, again, you wouldn't get that without a diagram. I don't think you get that without a diagram at all. It'd be a real tough thing to figure out. So it's not that the principle's hard, it's that we can just dress it up and make it so that, you know, there's a bit, you got to work a little bit harder for it. Any questions on that? I want to do one more, because occasionally when there's on a test type thing, so that's physics 2 stuff, I want to do one more. So let's say we have this. Boom, 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 boom. Do you know what a buffer is? You don't have railroad tracks in the States. At the end of a line, when it's going into a station, and it's not a through line, it's a platform line. It's going to be, it terminates there. You have a problem because sometimes if the train's going too fast, it could run into the platform and damage the train and kill people. So what they do is they have buffers, and buffer is basically, it's a big water tank really, and it has these little pistons on, and if the train comes in and hits the buffers, the water sprays out, and it slows down the train, takes the energy away. The water goes really high in the air, takes the energy away. And by using water rather than a spring, if you used a spring, if it came in at 100 miles an hour, it would stop and then would go back at 100 miles an hour, which is the last thing you want. So it's water escaping is like a frictional escape, so it's kind of nice. So I've got a buffer there, but I'm going to have spring buffer because it's like I don't know how to do water. So my K on my spring is equal to 8 newtons per meter. And here I'm going to tell you that my train is a 4 kilogram train, and it starts off here up this mountainside, which is 100 meters above the level. And then I should tell you that this is a radius of 60 meters. I'm going to tell you that that's a radius of 10 meters. I'm going to tell you that this here is going to be, let's have a look, 80 meters. And I want to know how much the springs are compressed. Comp of spring when train is stopped. That's what I want to know. I suppose I should tell you that this here is 70 meters. Frictionless track. Looks awful. Actually, what I did was I made it so complicated. I think you can guess that an awful lot of stuff in the middle we don't need. But I could make it so that I gave you detail about the stuff in the middle, and it was accessible. And I swear a number of people will be completely distracted by that. This is point A, this is point B, this is point C. We say mechanical energy at A equals mechanical energy at B. So then we get our kinetic energy at A plus our gravitational energy at A plus our spring potential energy at A must equal our kinetic energy at B plus our gravitational energy at B plus C, sorry. I don't care about B. At C plus our spring potential at C. So I come down here and I go, well, you're going to let this go. You let this go. So we have a half mVA squared plus mgHA plus 1/2 K XA is equal to 1/2 mVC squared plus mgHC plus 1/2 K XC squared. So I've got my equation written down. Well, VA equals 0. I just let it go. So that's 0 plus M is 4 times 10 times 100 plus, there's not even a spring at A, so that thing doesn't even matter. There's no spring there, so forget it. And a half times 4. It says 0 here, doesn't it? When stopped. So put 0 squared. Notice, I could just as easily not ask you for when it's at 0. I could say, how much is the spring compressed when it's traveling at 10 meters per second? So you'd put 10 in there as opposed to 0. And then I have plus M, which is 4 times G, which is 10 times H, and H on this side is 80. I'm going to have to put it on the line underneath. Plus a half times K, we said K was 8, times X, and that's what I want to find. That's what I want to find, that X squared. 4 tens of 40, 4,000 is equal to 0 plus 80 times 40, 4 eighths of 32, that's 320, that's 3,200, 320, 4 eighths of 32, 320, 3,200, plus 4x squared. Take that to the other side, that's going to be 800 is equal to 4x squared. X squared is going to equal 200. X is going to equal to the root of 200, which equals, root of 200 is seconds, square root 200 equals 14.14. That's a bit more interesting. Bringing in the spring, bringing in thing, putting some distractors in. It's a bit more interesting. Yep. That's more like a test question. Although I have been known to do some of the very simple ones. I sometimes think that, you know, I got to ask a variety of topics and a variety of difficulties, because sometimes people spend all their time just studying the hard questions. And if that's all I ask you, then they can just memorize a lot of things. So sometimes I will ask you about, like, the shape of a graph or something like that, because you've got to have depth of knowledge, not just being able to do the kind of fancy trick shots. You've got to be able to do a number of things. Cool. Cool. Let's look at this next bit, which is about the non-isolated system, or the non-conservative forces. We have rough snow. So no friction on the left-hand side and all friction on the right-hand side. And what we say is our change in our mechanical energy plus our work done by friction equals 0. Okay, so let's write that out a bit longhand. It's my initial mechanical energy plus the work done by friction equals my final mechanical energy. And there's a little bit of an alarm has to go off here, because people, including me when I first began, would put my friction on the second part. What I start with is equal to, oh, let's have a look, I paid for friction, I did this. And the problem with that is, because your work done by friction is a negative sign, when you put it on the other side, you end up with the wrong answer. So you gotta, because what you do is you take the negative work and you put it on this side, becomes positive, and it adds to the initial velocity, the initial energy, and that can't be right. So you've got to put a little arm there. Remember to put the work done by friction. If you're going to have the sign, which I think you should do, then it should go in before the equal sign rather than after the equal sign. 6 kilogram block slides across a smooth level surface. So here's my smooth level surface, 6 kilogram block. Constant speed of 9 meters per second. 9 meters per second. It slides onto a rough part of the surface and comes to rest. Let's show it here. 6 meters, 0 meters per second. After moving 12 meters through the snow, so that's 12 meters. What's the magnitude of the force of friction? Force of friction opposes the tendency of motion. The tendency of motion is to the right, so the frictional force must be to the left. Is it going to be a constant force? Yeah, probably. Yeah, I suppose it probably is. Maybe, yes, it probably is. So, fine. Even if it's not, I can do the average force of friction, but it looks like it's going to be constant. What I say is that my mechanical energy, let's call this A, plus the work done by friction is equal to my mechanical energy at B. So this is going to be only kinetic energy. So this is a half mVA squared plus force of friction minus FF times D is equal to 1/2 mVB squared. Let's call that VB. So then I get 1/2 times 6 times 9 squared plus minus FF, that's what I'm trying to find, times D, and D is 12, positive 12, is equal to 1/2 times 6 times, it's at rest, so that's 0 squared. So take the FF to the other side, 12 FF is equal to 3 times 81. 3 times 81 is 243. So FF is equal to 243 over 12, which is 20.25. 20.25 is the answer. Don't forget units. So the principle I'm using is the same. You know, it's what I have at the initial plus the loss of energy due to the work due to friction is equal to what I have at the end. Okay. Let me have a look. Yeah. Okay, let's draw a line. Power. Power is the work done over the timetable or my change in energy over my change in time. That's power. That's average power. So a student uses a pulley to lift a 9-kilogram bag 5 meters vertically. So here's my force. The job takes 12 seconds. Delta T equals 12 seconds. What power is required? P is equal to the work done over the time taken to do the work, which equals the force times the distance over the time taken to do the work. So the average power is equal to the force. Well, the force is going to be my tension, and assuming not much acceleration, going nice and slowly, that would be mg. So my T is equal to mg, which equals the mass, which is 9 times 10, which is 90 newtons. Stop. Let's have a look. I'm going to run out of time here, but I'll just do the best I can for a minute. So that equals, okay, the force, which is 90 newtons, times the displacement, which is 5 meters, over the time taken, which is 12. 9 5s are 45, 450 over 12. P, the average power, is equal to 450 divided by 12, which equals 37.5 watts. What I'm going to do, and so Watt is named after James Watt. So what is named after James Watt? Steam engines. I'll leave you to do this. This is basically the same thing. Electric motor is used to lift a 700 kilograms. So here's my motor. It's going to lift it by 120 meters. It takes delta T equals 1.5 minutes, which equals 90 seconds. And that's the catch. If you're working in minutes, you're going to have a real problem. So you've got to put down min. You've got to convert into seconds. So power is equal to the amount of work done over the time taken, which equals the force times the displacement over the time taken. So power is equal to, and it was 700 times 10 is the force, and the distance is 120 over the time taken is 90. And you work that out and you get whatever answer that happens to be. If I want to get the instantaneous power, then it's not delta W over delta T, it's dW by dt. And work is force dotted with displacement. So it's, well, d by dt of f dot ds, well, that's the same as f dot ds by dt. And ds by dt is velocity. So we end up with this weird situation where the force dotted with the velocity is the instantaneous power. So if I have a little spaceship and I have a force and I have a velocity, I can figure out what the power is been dissipated by that jet, by that little rocket. I'm so close. So spaceship fires its thrusters at T equals 1.25. The thrusters push. I'm going to. So here's this problem done, and basically we just ran through the things. Power equals force dotted with ds by dt. So the force times ds by dt cosine the angle, just using not the vectors now, but the magnitudes equals that. The angle is 0 because they're parallel to each other. So we get P equals FV, which equals 24 watts. And here's an example where I use IJK. So here's the answer for this, where we basically used the dot product and we left it in vector form, and we just mathematically ran through it and got our scalar answer. A dot product is a scalar, which is 29 watts on that one. And then this last bit is basically about the definition of the watt, and the watt is a joule a second. What is the visualization for a joule? It's taking an apple and lifting it onto the desk. That's a joule of work, a newton through a meter. 1 joule of work is lifting an apple onto a desk. An apple on the desk per second is 1 watt. So 1 watt is a very small amount of power. And the alternative, which you'll come across, is the horsepower, which is, it turns out, 746 watts. Well, not all houses are the same, and so that's just an arbitrary value which we've agreed upon. Don't get freaked out about that. I'm going to stop there.